Reactive power, apparent power, real power are actually very easy to understand, and I'm going to prove it to you in this video by making you understand it. When you're done with this video, you will understand how they work intuitively, or your money back, guaranteed. Okay, so in this case here, I have this electric motor, I have a transformer to reduce the voltage from mains, and I have this capacitor. So think of it sort of like a basketball, right? This will represent my basketball. Now when I dribble a basketball up and down, it is converting power back and forth between potential energy, in other words stored energy, right? So when the basketball is at its highest point, it is just before you touch it with your hand. In fact, if you didn't have your hand there, right, it'll come up and stop and then go back down, right? So that is the point of maximum stored energy. We'll call it potential energy, but stored energy is a little bit easier to understand in terms of language in the human brain, right? So it has the potential to fall that distance, but it's not actually moving it as it comes up to the top. It's stationary, right? And then at the bottom, just as it hits the ground, it is at its maximum speed, so that's its maximum kinetic energy, but you'll think of it in terms of momentum. It's easier for your brain. Maximum momentum, but the potential energy is zero. The stored energy is zero because there's no distance off the ground, ergo it has no potential to go anywhere, okay? And so that's, as this basketball bounces, we're going back and forth between stored energy and momentum. And that's exactly what happens in terms of reactive power. That is what reactive power is. This capacitor stores energy, just like height on your basketball, and then this is an inductor, so this has momentum. Now, this is a little bit misleading because obviously this spins, right? So this rotor, this impeller has momentum, but do not be confused. I'm talking electrical. So for example, it is possible to have an inductive load without a spinning rotor. So bear in mind, my metaphor here is imperfect, right? But the momentum of an inductor is unrelated to whether or not you see spinning with your eyes, right? So this, for example, an ignition coil, an automotive ignition coil is a great example. There's no rotation, nothing is spinning in an ignition coil, but it has electrical momentum, and that's what causes the spark. When an inductor goes open circuit, the electricity that was flowing in there wants to continue flowing, sort of like the way that a flywheel spins, right? So an inductor with no electricity moving through it, your flywheel is not spinning, right? But you think about if you spin up a flywheel, it's hard to slow it down, right? All the energy you put into spinning up the flywheel, you have to take that energy back out in order to slow it down. It's the same thing with an inductor, right? So in a car, power is, your 12 volts flows through the ignition coil, and so as the power begins to flow, it doesn't flow instantaneously, right? Because again, this is a flywheel. So 12 volts has to be applied to that ignition coil for a period of time, and the current slowly rises over a period of like microseconds, right? But that basically is spinning up your flywheel. So then when your car wants to spark, when your computer wants the spark plug to fire, basically what it does is on the primary, it just goes totally open circuit. And so you get a voltage spike, sort of like a water hammer. Now this is a little bit more obscure. I don't know if you've ever experienced this, but if you have the faucet in your house, if you have it on full maximum water, and then you immediately shut it off, sometimes in certain houses, the pipes and the walls will clank. And that's a water hammer, right? That water has mass, therefore it has inertia. So when you shut off the valve, it wants to continue flowing. It's like a train, right? So the water immediately at the valve comes to a screeching halt, and then the water behind rear ends it. It's like a series of cars rear ending each other. Ding, 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 ding. And so all the momentum of all the subsequent cars, and then it causes the pipe to clank because all that energy is trying to dispel somewhere, and so the pipe rattles, okay? So it's the same thing. Primary goes open circuit in your car, and so electricity is flowing through this ignition coil. It has momentum. The electricity itself has momentum, even though the ignition coil has no moving parts. And so that's what causes the spark plug to fire. You get that water hammer, but electrical. The voltage spikes because the current has dropped to zero, but the current doesn't want to drop to zero. So the voltage rises in an effort to try and keep the current flowing, right? And so that's where the spark plug sparks in order to discharge the momentum of that flywheel, okay? And so that is your reactive power, okay? So this capacitor charges up and it stores, you know, it's like a battery, but better, except in terms of, you know, energy density, but it's basically the ideal battery, right? Power goes in, stores power, and so then basically there's a point where zero current is flowing through the inductive load, and all of the power is stored in the capacitor, and then the capacitor obviously is connected to the load. You know, these wires are connecting it, right? So this stored electricity wants to go somewhere, so it does. It flows through the inductor. And so there's also a point, so we've gone from maximum stored energy now to maximum momentum or kinetic energy, right? So there's also a point at which this capacitor, it discharges, and eventually this capacitor is empty. But now there's amperage flowing through this motor. And so that amperage, again, not the rotor itself, but the electricity that you cannot see, has momentum. And so then what it does is it charges this capacitor backwards, right? Just like this capacitor discharging bounces, and then it kind of charges it backwards, right? You know, in other words, the basketball's traveling up instead of down, right? So then the momentum of this electricity then flows backwards into the capacitor, charging it up. Now, it doesn't charge it up as much, just like your basketball, it bounces a little bit less every time, right? Same thing here. So it'll charge the capacitor, but much less than it was charged originally. And then this will discharge into that, and then that, the momentum from that will be stored in this, and then this will discharge into that. That is reactive power. It's your basketball, okay? Now, real and apparent power. Those terms are the most confusing, but think of, again, let's go back to our basketball analogy. Your hand is the real power, right? So the first time you throw the basketball, you know, it has stored energy from when you picked it up, right? So that you're combining your throw, you're pushing on it with your hand to replace the energy lost to the system as heat, right? You're pushing, because if you just drop it, it comes back up lower. So you want it to come back up to your hand, right? So you give it a little bit of a push. So now, you know, the basketball bounces and it returns to your hand. Every time you bounce the basketball, your hand is only introducing real power, right? You're just giving it a gentle push, right? It's not a lot. You're pushing gently on the basketball, but it's enough to replace what is lost. That way the basketball bounces up to the same height, back up to your hand again, every single time, right? And so the force on your hand is the real power. The apparent power is the basketball moving back and forth, right? There's a lot of crap going on here. There's a lot more energy bouncing back and forth than your hand is capable of introducing. And so that's with this system here, right? Electricity is bouncing back and forth, just like the basketball, between kinetic and potential energy, back and forth between the capacitor and the inductor. That's your reactive power. And if you take the real power coming in from your mains supply, or whatever it is, real power coming in plus reactive power, that's your apparent power. Now, if I take this multimeter and I measure the basketball bouncing, I'm going to see a bunch of energy. And that's between power coming in from your hand, but also these two things, right? But if I measure it somewhere back here, right, I'm measuring probably, and you want to be careful, right? Obviously, I don't want to misinform you. You got to be careful not to include the capacitor in your measurement. So in this scenario, this transformer is reducing mains, and I have the capacitor on the secondary side. So I'm not certain that this is perfect, but bear in mind, in terms of the metaphor, this is probably close, right? I'm just measuring power coming into the system, right? We're isolating this reactive power over here. We're not measuring it. That's your real power. And then your apparent power is if you just measure the system itself, you know, the basketball bouncing, basically, there's a lot going on here. So this is basically, this capacitor is adding extra amperage. Now, if I were to take this capacitor out of the system and we just have the inductive load and no power factor correction, then this is going to be your, I believe, your real power, right? And the power factor is going to be bad without the power factor correction of the capacitor. Basically, but what we end up doing here when we add this capacitor to correct the power factor, we're adding amperage. So basically, if I measure just this capacitor with my ammeter, again, that's your reactive power, but that's, you'll see, I don't know, an amp or something, right, or a couple of amps. But what those amps are doing, again, is they're just bouncing back and forth right here with the capacitor and the inductor contained within the system, and it doesn't affect APS at all, right? So when you bring your power factor up to the correct number, and so that gives effectively this motor some extra amps to run. So it's getting fewer amps from mains because the power factor is correct, and it's getting a few supplementary amps from this capacitor. So this allows it to bounce effectively, and then this you're giving it just enough power to bounce. And without the capacitor, it gets kind of weird, with the phase shift. And by the way, I made a little bit of a mistake here, and I want to interject this because this is important. Without this capacitor, basically your basketball is still going to bounce, right? In other words, this apparent power. Let's say for example, we'll make up numbers. Let's say you have 2 amps. Again, these numbers are imaginary. 2 amps flowing, bouncing back and forth between this capacitor and this motor, and then we have another 2 amps coming in from mains, and that's the real power or whatever powering this system, right? So there's 4 amps in apparent power, 2 amps in real power. Well, if we get rid of this capacitor, motor's still taking 4 amps. Okay, and so what happens is when this power factor is wrong, when it's not corrected, this motor is going to find something akin to a capacitance, and so those 4 amps now are flowing through mains. So when I stick a capacitor here, the power company is sending me 2 amps, and that's it. When I get rid of this capacitor and the power factor's fucked up, the power company is sending me 2 amps in real power plus another 2 amps in reactive power. In other words, this basketball bouncing, even though it's not bouncing here, it's bouncing down that line. And that's why power companies hate bad power factor, right? So for example, if you have a gigantic factory, and again, you as a consumer, it's not as important. You don't have enough motors, basically. You don't have enough inductive load for it to matter. But if you're a factory, if you have a ton of motors, right, and you have 0 capacitors, you got to think in terms of, I don't know, it might be 200 amps, say, again, I'm making these numbers up, 200 amps coming in real power, plus another 200 amps here. And by the way, this number is probably low. 200 amps is actually pretty low. Another 200 amps here in reactive power. Well, if you get rid of this, now you have 400. Instead, you can have 200 amps in real power coming in, or you can have 400 amps in apparent power coming in. Now, in either situation, you're only getting billed for the real power. You're only getting billed for the 2 amps in the smaller analogy or the 200 amps in the bigger analogy. That's all you're paying the power company for in either scenario. But when you double the amount of amperage flowing down these lines because your power factor's messed up, right? That means at some point APS has to have bigger wires, right? They can't have wires rated for 200 amps if you're sending them 400 amps, an additional 200 in reactive power. So they have to oversize the wires, oversize the transformers, etc., right? And then this bouncing happens, all the way down APS transmission lines. I say APS, right? Obviously, I'm in Arizona, Arizona Public Service or whatever. I shouldn't say that because that's a local power company, but use your imagination, right? The power company. That basketball bouncing, it runs down their power lines to gosh only knows where. So that's why the power factor correction is important. So I don't want to mislead you again where, okay, the reactive power is contained within the building. Well, the reactive power is contained within the building when your system is correct, when you have the correct amount of power factor correction. And so if you're a little bit undersized on your capacitor, right, I'm going to hide 10% of that capacitor behind the transformer where you can't see it, then say we have 200 amps in real power coming in, 190 amps reactive here, and then 10 amps reactive flowing into the power grid. So that's 200 amps in real power, but 210 amps in apparent power, because my power factor correction isn't perfect. Now, again, if you're that close, in terms of percentage, you're doing pretty good, I think. Again, I'm not a lineman, right? I'm maybe not the the proper guy to ask, but basically, you want those amps to be bouncing back and forth within your building rather than making the power company mad and bouncing in their lines. That's a lot more current their lines have to handle. Whenever you think of reactive power, just think at your house or at the factory, whatever it is. Self-contained within the factory, reactive power is the number of amps flowing back and forth between the inductive and capacitive components of the system, right? Basketball bound, reactive power. Real power is genuinely how much power it takes to sustain this bounce, and then the apparent power is all of them together, reactive and real. And the apparent power is higher because, again, you see here, this ammeter, you see how this is a Y, right? So we have this white wire goes off to my motor, and then we have these two wires here, right? One goes to our quote-unquote mains supply, power in, and the other wire goes to our capacitor, right? So each wire to the motor, you'll see there's two of them, each one has two. And that's what the apparent power is, and that's why the apparent power is higher, is I'm measuring between my load and the capacitor and the load and mains. So hopefully that's how it works in my brain. Obviously, this, in terms of a kind of a basketball analogy, I don't totally think of it in terms of basketball, but that'll help you understand. I think of it in terms of electricity bouncing back and forth between these two parts. And that makes it very easy for me, and therefore, reactive power is much more intuitive in my brain. This is a way that basically what we're doing is we're taking these electrical properties and we're changing our wording so that our human brain can understand it. And you can do this with any complex topic, right? So the hardest part is understanding the topic itself. Once you finally understand the topic, you can then in your brain kind of simplify it, right? You got to be careful. It is human nature to simplify things, but you don't want to simplify it too much where you actually hurt the meaning and you lose some of the nuance, because some of that nuance is critically important. So that, when you're a teacher, that's what your job is, to understand. Hopefully, I haven't made any mistakes, right? So hopefully as a teacher, I understand these concepts at a high enough level. And then once I really understand them, then you can, don't think of it necessarily in terms of simplifying, think of it in terms of recontextualizing, right? So I don't think I'm necessarily simplifying this topic, because hopefully you understand all of the components, right? Simplifying, I might leave something out. But recontextualizing, there are certain things like bouncing basketball, or you can make it whatever sort of analogy that you like, right? A spinning flywheel, if you grab the shaft with your hand, it's going to twist your hand, it's going to hurt. You cannot, it's very difficult to stop a flywheel if you've ever tried. And if you skid your hand a little bit like a brake pad, your hand gets hot as you dissipate that energy, right? So we're taking something that's more intuitive and natural to your brain, like a basketball or what have you, and we're reapplying it to these electrical systems that you can't see. That's what's so confusing. These terms, they seem intimidating, and you can't see the electricity. These wires, nothing's happening. So for me, I sort of, it's almost like a type of schizophrenia, right? Where just based on vibes, I imagine this electricity. I schizophrenically hallucinate the electricity in my mind, right? And so you imagine, basically, just the power bouncing back and forth. And again, it's confusing a little bit too, because AC is reciprocating. So positive and negative are constantly flipping. So that's a alternating there, but it's also alternating in terms of kinetic and potential energy between these two parts. So, you know, it's a little bit of a compound alternation there. But anyway, yeah, hopefully that makes more sense to you. And if not, if you don't understand, now I owe you your money back. So, I don't know, send me a fucking strongly worded email or whatever. Okay, good luck, subscribe, you know, like, I'm poor, I'm dying. Help me get monetized, please, I'm begging you. All right, good luck.
Yeah, man. There it is. So this is super crazy dangerous. That right there is Balin Mania, and we are going to do something really stupid today. This is a terrible idea. Balin might die. It's making me uncomfortable. Go, Balin!
You riding this?
What the fuck is happening?
Balin said not to talk crap about this camera. It's a piece of shit.
This is so unbelievably sketchy. Why must you put me through this, you jerk?
That's the power of really old engineering.
It'd be nice if it didn't kill me. It's not required.
I felt it fucking pop.
Make a wish, everyone. Make a wish. Not okay. You went too far. This guy, man. This guy.